What is this, chapter 4? This week we are covering plate tectonics, but before we talk about plate tectonics, we have to back up and talk about what is inside the Earth and heat transfer, so we know what the Earth is made up of and how things are moving. So these are words that were in the textbook reading yesterday. Yesterday and today you did the worksheet. If you have not already written these words down, you should write them down now. So the crust, of course, is the outermost layer of rock on the Earth's surface. Basically, all of the Earth that we see is the crust, and the crust actually goes under the ocean as well. It's made up of rock, minerals, and this represents all of Earth's surface. Pretty easy. You know before you walked in here this week what the crust was. Now, lithosphere. Lithos means rock. Sphere means sphere, obviously. So the lithosphere is the uppermost layer of the mantle, which is very similar to the material of the crust, and the crust. So the reason there's a separate name for this, the crust obviously is that topmost layer. The lithosphere is what the plates are made of. You'll be reading further on in the chapter, there are actually big sections of the Earth crust that move around. And this is what causes earthquakes and volcanoes. That's kind of the whole big idea for the week. We just have to back up and do this stuff first. And we'll have a diagram in a minute here so we can look at this. But so plate tectonics are plates of the lithosphere. So then the mantle is actually divided, so it's crust, mantle, core. The mantle is divided into three layers. The uppermost mantle, which is here, and then the asthenosphere. The asthenosphere is the middle part of the mantle, and it's very strange because even though it's kind of solid, it has this kind of silly putty-like texture. You guys all know silly putty, right? Silly putty, even though it's kind of a solid, if you leave it sitting on the table, it will slowly melt into a puddle, right, by the next day. It'll be flat. Silly putty. Yeah. And so the very strange thing about this portion of the mantle is that because it's not a true solid, it can have convection currents. And this is what's going to be moving the plates of the Earth. Okay, and then we have the mantle towards the core. The mantle is the largest part of the Earth's interior. Again, we'll go over that on your picture here in a few minutes. And then the core, again, you probably all have heard of the core and know what it is, but the core is actually divided into two layers, the outer core and the inner core. And so this is very interesting because all of the drilling, all of the mining, all of the excavation humans have ever done is all only in the crust. So we have to talk in a minute about how we know what's going on below the crust. But the core, there's the outer core, which is molten metal. It's very high temperature. It's high pressure. It's believed that the magnetic fields of the Earth are because of the core. So planets that don't have a liquid core don't have magnetic fields and don't have earthquakes and volcanoes. It's melted rock. It's iron and nickel. And then the inner core, interestingly, is also melted iron and nickel. It's even hotter, but is under so much pressure that the molecules can't move, so it's actually a solid. And these were your first direct evidence and indirect evidence. Direct evidence of what we know about the Earth is from drilling. We've drilled down, we've looked at it, we've sampled it. And then indirect evidence, how do we know that the mantle is silly putty texture and that the core is liquid and solid? How do we know that? How could we possibly know if we've never drilled that deep? What was that? Indirect evidence from earthquake waves. So in the similar way that you could use sonar, right? Ships can use sonar. They send down a signal, it pings back up, and it tells them something about what's below. In a somewhat similar way, earthquake waves going through the Earth, waves travel differently through solids and liquids. And so we know from the way they travel through the Earth, that there is, in fact, a liquid and a solid core. And we've got a little more detail on that here ahead. You guys have that, or you need a minute? Need a minute. Okay. All right, so next, if we take a look, this is the worksheet you just did. This is pretty straightforward as we go over this. Pretty easy, right? What's number 1? Number 2? Number 3? Number 4? And if you had to draw the lithosphere, where would that be? The crust and the outer mantle. Okay, and then the 2 types of evidence, and we just really went over this, 2 types of evidence would be direct, when you're actually drilling, and indirect. Indirect evidence, obviously scientists have to use indirect evidence sometimes in order to, because we can't always study things directly. So we use indirect evidence oftentimes for like for instance, obviously we can't see into the Earth. There's no way to drill any deeper into the Earth because of the heat and pressure. So oftentimes scientists use models or indirect evidence. And in this case, we'll talk about a little bit more detail, but the indirect evidence includes earthquake waves and such. So compare and contrast the asthenosphere with the lithosphere. You guys all got that, no problem? We're going to talk about those 2 layers a little bit more. What's one of the biggest difference between asthenosphere and lithosphere is in terms of the texture and what it's made up of? Yeah. Yeah. Yeah, exactly. So the asthenosphere is more putty-like. The lithosphere is actually more rock-like. So that's the big difference. Okay, and then you guys got all these? Awesome. All right, guys, what are the correct letters? Is this right? Okay, so double check, make sure you have those answers correct on your worksheet. These are good words. Actually, this week's quiz will have a little bit of a review of rock types. So this would be a good chance to review basalt and granite, which is something that people struggled with last week. Okay, and now this worksheet, again, this is really mostly review. Real quickly, and then on the next page I'm going to explain it a little bit more. Is this conduction, convection, radiation? And how do you know? On the next page, guys, I'm going to explain each one of these, but how about this one? Conduction, and it's really not the best picture in the world, but if the burner is hot and it's touching the tea kettle, and the tea kettle is touching the water, that's how it's heating up. And then, so this one, the swimming pool, is being heated by the sun. The sun is obviously not touching the swimming pool. We're going to go over this and this in the next thing here. So, okay, so a quick summary of the 3 types of heat transfer. Radiation. So radiation, and many of you guys had read the textbook definition, which is the transfer of heat through electromagnetic waves. Well, that includes all of the energy from the sun. And so when we're talking about radiation generally, it's energy that can travel through empty space, because heat itself doesn't, but energy does. And then that heats up the Earth. The sun is 93 million miles away, but it is the main source of heat and life on Earth because so that's that energy source. The plants use it to make food, etc. But so radiation travels through empty space. It does not have to have matter. It does not have to be touching. And it's very different because of that. Also, anytime you have a heat source that's glowing, a glowing fire, electric burners or electric things, yeah, when they're glowing and that heat is coming off of it, that's also radiation heat. So yeah, incandescent light bulbs give off radiant heat as well as, so they can heat that way too. And they can also heat other ways as well. So convection currents happen in gases and liquids. It has to happen in gases and liquids. It's a current. It's flowing. And the way this happens, and this is the rest of that question on the front side, the way it happens is as some areas get warmer, the molecules move faster, they spread further apart, it's less dense, and so it rises, and then it cools off and it becomes more dense and sinks. And so the example of that, you can imagine currents. So if it's heating here, the pan of boiling water, this is conduction where it's touching the burner, but then the water heats evenly through convection, and it actually gets into that kind of rolling boil where you can actually see the water moving. Convection is also happens in our atmosphere. The sun, through radiation, heats the surface of the earth, and then the air that's closest to the warm rocks heats up, and then you get air circulation. Happens in the oceans too. So it happens in liquids and gases. And then conduction, heat transfer, the two surfaces must be touching for conduction. Yesterday when we talked about heat transfer, a lot of people associate the word conduction with conducting electricity. You can think of it in a similar way because for electricity to conduct, it has to have a circuit that's complete. It has to be able to touch and transfer. So conduction, heat transfer, and the two surfaces must be touching. So then we can take this and apply it to what is happening inside the Earth. We'll come back to that one. What's that? Oh, in a minute. So here inside the Earth, we have, what's the hottest part of the Earth? The core, the inner core. So this is extremely hot. And so that touches the outer core. The outer core is liquid, so you can get some convection. So you've got conduction, convection, and then that's going to touch the mantle. And the mantle, because of its very strange texture, the mantle actually has convection currents in it. So this is going to be very hot, and the hotter parts are going to come less dense and rise. So you're actually going to get convection currents in the mantle. And then as those convection currents move upwards, then they cool off. And so you get these patterns of convection currents like this. Then that top layer, which is the crust or the lithosphere, the top of the mantle and the crust, those can actually move because they're separate plates, and those convection currents are actually moving the plates of the crust. A little bit confusing, but we're going to continue to talk about that throughout the rest of the week. This picture from the textbook, going back to something we were talking about a few minutes ago, the indirect evidence of how we know what the inside of the Earth is like when we've never dug deeper than the crust. When an earthquake happens in a particular area, just like any vibration, any energy wave, it travels through the crust, and so it'll be felt further away, and it can be felt at points all over the world. But some of the places are very predictable as it passes through material that's very similar. But then you see how these things kind of change, like this. And some types of earthquake waves, there's three main types that we'll learn about in a couple weeks. Some types of waves will not travel through liquid because the liquid just stops them. So that's how we know that there's a liquid core. Okay. Make sense? the big idea there is just that's how we know what we can't see. Okay, so that's what we just talked about. And then this is again, it's a picture from the textbook. And I don't care if you know how deep each layer is in miles or in kilometers, but this is just generally for, kind of scale so you can see the crust. There's crust under the ocean, which is oceanic crust. There's crust in the continents. So under the crust or under the oceans, it's more dense because it's cooling differently, and that crust is about 2 miles deep. The continental crust is like is about 35 miles deep. So that's what you're trying to drill through. The lithosphere, the plates, the crust of the upper mantle, asthenosphere, simply poly texture, and then the core. And so that kind of gives you that break apart that we talked about earlier. Okay? All good? Okay, so we just talked about conduction, convection, radiation, and let's take a look at what you have in front of you. You have a little setup like this, and what we're going to do, we're going to demonstrate some convection currents. So first of all, take this jar. Do not open it. It has something called convection fluid in it. If you pick it up and gently tip it back and forth, it won't be clear like water anymore. It's going to look really awesome. And then I'll show you what's going to happen. We'll come back and look at it in a few minutes. But what I want you to do, you should have room on one of your worksheets where you can maybe draw a picture of this. Okay? On one of your worksheets or in your notes, draw this setup, and we'll talk in a minute about what happens. So what you should see with the convection fluid, this is going to, of course, represent the core. And then I heard a couple people describing it like it looks like a volcano or whatever. But basically, this is, in our example, we have some radiation and some convection. But in the actual Earth, it's conduction. And so then it gets hotter here. The fluid gets warmer and starts going off this way and this way. And so you get a little bit of a pattern, and you can see the convection currents here. So this would represent the mantle. And if you could put little things here on the surface, if you look down from the top, you might actually be able to see the surface of the fluid moving. But this is basically, it's just a little convection model, pretty simple, but you can see an example of convection happening.